front that side-ish. Front. You got it. That works. No problem. Let me get this board set up. Board problems, erasing. I'm not starting until 4:30. Just get set up. I want to make sure everybody can see the document and the board. Perfect. And don't worry, I have every problem we're going to go over, I have a solution to, which I'll upload as well. So you can follow along and whatnot.
Before you officially start, I'm checking on here, just to make sure that the audio is coming in.
I won't start until you tell me.
I'm not sure what you want to do this mostly on the camera because you can see the heads like kind of blocking the board. So
Gotcha.
just,
I
if
could
you want
probably
to
move
find
it
a
up a little
space,
Like I'll put it in the center up there, maybe.
yeah, like in this space.
I got it. I'll put it in that space. All right, cool. Awesome. Just let me know. I'm not gonna start until 4:30 or whenever you tell me.
Okay.
Can't stop looking at that thing. I keep blinding myself every time. For those of you that are just coming in, I ask you kind of move up forward because I want to use the board really bad, and I don't want to write on this because one, it's upside down, and two, it's just kind of annoying. So don't worry, I already have all the solutions and I'll upload it to my Google Doc, all the things we'll go over, so you can follow along, write down. I'm going to ask for participation and whatnot, but just know you will have the solutions after this. Okay? Awesome. And I can't zoom out. Great. Put this over there. Here. Can everybody see this board? Awesome. Somebody can't, let me know. Whatever. This session is being streamed and recorded online, so you can watch it later and whatnot. That's why for all the mics and everything. I hate microphones, trust me, I wouldn't be wearing it otherwise. So, there you go. Turn light on. Light? Haha. No. There. Too much. No, I wish I had two boards. That'd be nice. So how are you guys doing today? Stressed, studying, exhausted? that are coming in, try to fill up front because I'm going to try to use that board. I'd really like everybody to see that board. This gives me more space. If it really comes to it, I'll use the dock cam. I just, you know, it's upside down. It's kind of annoying. Up front
You
right
like
there is
that?
my solution dock. Just be careful. I need that up there. There. I'll move that out of you guys. I'll put that out of you guys. Doesn't do you any good in answers. Maybe. Still a little down. Switch? Yeah, sure. Switch to that one? Yeah. Awesome. Is this on? Now it is.
This one's for our stream and this one is in-house.
So,
Just wear both of them.
wear both?
Yeah.
What if I don't need, what if I talk loud and don't need that?
That's fine.
Awesome. I'd rather not use a mic, then I can hear just noise.
Hey,
It's
fair
one of
enough.
those I just,
If everyone else will be fine in that
yeah,
room, then we're
I'll
fine.
ask first.
Yeah.
If not,
but
then
that's
I'll
for
use
our
that.
stream, so that's good.
Got it.
Thanks, man.
Can everybody hear me without the mic? Yes? No? Maybe so? Well, I'm going to be standing up there, so. Awesome. I hate microphones. This one's for the live stream. Let me make sure my markers work. Does this work? Hey, my markers work too. That's awesome. Do you mind if I put my solutions dock like there-ish? Awesome. So I have some desk space. Well, all right. Can everybody hear me? Yes, no, maybe so? It's 4:31, so let's start. Like it says at the top of this, which you can't see anymore, I moved it down. This is a combination of problems that I think are good for your final. Do not just use it to study for your final. I cannot emphasize that enough. I will go over a good mix. I'm going to try to get this done in an hour and a half, so you have a half hour to ask questions, go over problems you want. I mean, it's your review, not mine. So let's. I'm also going to ask for some participation. I don't like doing all the work myself, honestly. So I need your help. Awesome. So the first question up there is write a formula for the compound formed between potassium and sulfur. So first thing, how do we write a compound between the two? How would we normally write a reaction or compound? You know, I am going to use the mic because there are more people in here than I thought there would be. Look at this thing. Does this thing work? Yes? No? Hey, it works. Don't like it, but it works. Now I feel really wired up. All right, this one's going to go here. I feel like a newscaster with like 5 mics under me. All right, can everybody hear me even in the back? Whatever. Awesome. So we're going to try to write a formula between potassium and sulfur. So how do we do that? Volunteer. Yeah.
Look at your charges.
Exactly. Look at your charges. So you need your periodic table. And what's the symbol for potassium? K. And what's its charge? +1, +2, plus what? +1. How do we find that? How do we find it? Yeah, exactly. It's in group 1A of the periodic table, so charge +1. What's the charge on sulfur? 2-. Exactly. It's a nonmetal. It's in group, that would mean 8, 7, 6. It's in group 6A of the periodic table, so it has a charge of -2. So how do we figure out what combination would work? We bring these numbers down. So this one's going to have a 2 here. We're going to bring this number down here. It's going to be 1. So then we're left with K2S. Questions? Reaction writing, or not reaction writing, compound writing. Yes, no, maybe so. Awesome, good. Second question. This one is a really, really poorly written question. I took it from something else. I really don't like it. But it does illustrate a good point that you need to know. What is precision? Precision. What is it? Exactly. It's how close the grouping of numbers. Say I measure something, and I get, let's say I measure something, and the accepted value is 0.5 grams. Okay? First time I weigh it, I get 0.6. Second time I weigh it, I get 0.0 or 0.601. Third time, I get 0.602. Is that precise or accurate? Precise. Precisely. Ha. They're close together. Your trials are very grouped close together. So say I had a trial that I got 4.9, I got 5.0, and I got 5.2. Is that precise or accurate? Accurate, because it's going to average out to be roughly 0.5 grams. This one's closer together. This one's more accurate. Which one's better? Accuracy, precision, what? Accuracy? I believe precision is better because it's comparable to your standards. You know you're right. You know your equipment is reading it steadily. It's better to be steady than to be all over the board. Okay? Make sense? Precision versus accuracy. I don't like this. I mean, there's a typo. It should be closer to 0.1 grams. Or, I mean, 1.0 grams. And then which one's more precise? Which one's accurate? Okay? That's that question. I don't like it, so we're going to move on. Okay. Number 3. We're moving right along here. Which is not a salt? Right? What is the definition of a salt? Anybody? It is an ionic compound, yes. Good. Pretty much. It's an ionic compound that's formed between the reaction of an acid and a base, essentially. Okay? So which one's not a salt? What is KCl? Better question. What's an ionic compound? A metal and a nonmetal. Good. If you have answers, just yell them out. You can raise your hand, but just yell them out. It's a metal and a nonmetal. So the definition of salt is it's an ionic compound, essentially. So the first one, is it a salt? Letter A. Is it a salt? Yes. We're looking for which one's not. We'll skip B. Spoiler alert. C. What is it? It's magnesium nitrate, I think. That's a 3, I think. Yeah. Is that a metal and a nonmetal, essentially? Is that a salt? Yes. Cool. So that one's a salt. How about BaCl2? Salt? A salt? Cool. That one's a salt. How about NaClO? I think that's a 4. Yeah. ClO4. Salt. Metal, nonmetal. Cool. How about HCl? What? That's an acid. We know salts have to be formed from the reaction of an acid and a base, forms salt and water. That is the acid, so it's not obviously not a salt. So look for the one that's not a salt. So HCl is the answer to that one, which is not a salt. What's the name of that acid? Hydrochloric acid. Exactly. Binary acid. Hydroic acid. Awesome. Let's keep moving. Let me move this thing down without blinding myself. Which way? It's this way. Check that out. I'm just going to have to come back up here anyway. I calculate the work energy gained or lost by the system when a gas expands from 15 liters to 35 liters against a constant external pressure of 1.5 atmospheres. Okay? I'm going to give you guys a chance. Try it. I'll give you like a minute and a half, 2 minutes. Try this problem. All right? Give it a shot. Seriously, I want to see everybody try. I'm nice. There's your hint. Give it a shot. You got another minute, 2 minutes. Cool. What? Is it A? Yes, it A. It might be. We'll go over it in a minute. Give it a shot. Give it a go, give it a go. Can everybody see that, or do you want me to zoom in? Zoom in. Awesome. If there's anything like that, let me know. If you can't hear me, if you can't see anything, let me know. Let me figure out how to zoom in first. There it is. Better? Yes? Awesome. Zoomed in. Coming down. Let me see. There's a black marker over here. Let me try something slitter. Does this work better? It works okay. We'll try it. Does this one work better? It works. Either or. Alrighty. I gave you 2-ish minutes. Let's go over this problem. So, what are we looking for in this problem? Come on, yell it out. Work, exactly. And what is work? It's doing something, hence working. So it's either doing something or have something done to it. So I gave the formula as my hint here. Work equals negative pressure times delta V. What does pressure have to be in? Joules per atmospheric liter. So yes, both guys are right, both people. So it has to be in joules per atmospheric liter. That doesn't help. Let me try a black marker. Joules per atmospheric liter. How about volume? What does it have to be in? What? Volume. Liters. That was a trick question. It's already in liters. This one has to be in liters. The liters cancel, and that's why you get this. So when we plug in, we get work is equal to negative pressure, which, what's our negative pressure in this case? Wait, what is it? Negative 1.5 atmospheres. What does it have to be in? Joules per atmospheric liter. If you notice, there's a conversion factor down there. 1 liter equals 101, it's 101.3, but close enough, joules per atmospheric liter. So it's work equals 1.5 times 101.3, and then that's multiplied by, that's our pressure. Well, there's a negative in front of here. Negative. And that's multiplied by our change in volume. So how do we find our change in volume? Subtract the final from the initial. So what's our final? 35 minus what? 15. So what is this thing doing? Is it expanding or is it contracting? So what's our sign going to be on it? Before you even calculate, what's the sign? Negative, negative, positive, what? Yeah. Seeing this? Do you want me to go up there? Yeah, I could try it on there. Let me give that a shot. The problem is it's like upside down. Let me see if I can move some things without totally unplugging the whole thing. I don't know how someone did this before, but whatever. All right. Let's take a look at this. This is a pain. Hold on. That's a little better. Better? All right. So our formula is work equals negative pressure times delta V, volume. Pressure, volume. Work equals negative pressure times delta V. Pressure has to be in joules per, of course that's not going to work, ATM times liter. That's an M. Okay? And that's multiplied by our volume, which is in liters. So liters cancel. You're left with joules per atmosphere, and that's what you want. All right? So we already said our pressure is negative 101.3 times 1.5 atmospheres, which is what we're given in the question, times our change in volume, which is our final, minus the initial, 35 liters minus 15 liters. I hate this mechanical pencil. So we know, since it's expanding, our sign on work is going to be negative because the thing is doing work. If you do work, I think of it this way. If you do work, you lose energy. Okay? This is doing work, so it's going to lose energy. Cool? Questions before final calculation? Questions, comments, concerns? Everybody understand? Awesome. So when we calculate this out, we get negative 3 kilojoules, roughly. Our answer will come out in joules, and then we convert to, if it's kilojoules, convert over. If it's joules, leave it the same. Make sense? Awesome. Let me see if I can set this up so it's a little bit more conducive to me working with this. Just a tad. Try that. That one kind of doesn't. What? Can I flip this? Can I flip that over there and move the computer? Because
What you trying to do?
this is upside down. Can I flip this to where the computer is? Like, move this on that side, because that's how it was this morning.
Oh, okay, yeah, you can try it.
Yeah. Yeah, let me give it a shot. It's kind of hard to write like that. All right. Hey, that works. Awesome. Thank you. Perfect. Let me figure this out. Zoom out. Awesome. So Any questions on that before we move on? Questions, comments, concerns? Awesome. Let's move on. Yeah, question.
If your units are supposed to be in joules or atmosphere times liters,
Yeah.
how come your file? Or,
It's just in kilojoules, you're wondering?
no, like you have 1.3 times 1.5. That would
Yeah.
be joules times atmospheres instead.
It's joules per atmospheric liter. You don't have to worry about the atmospheric liter part. Just leave it in joules. Okay? What? Yeah. Don't no. It's that fraction is the units. It's not the thing. It's just the units. Okay? Cool. It's one thing multiplied by another thing. You don't have to put in a fraction. All right?
I have a quick question.
Yeah.
Why is if W is negative and pressure is always going to be negative, how come it doesn't cancel out and be positive?
Work, okay, in the equation, we figure out that work is negative through this. That's why when we have a negative volume, it's not the pressure negative, it's the whole thing on this side is negative when volume is positive. When it's expanding, you're going to have a positive volume, which means it does work. That's why this is here to flip it. It's already part of the equation. I was just asking a conceptual question, okay? All right, let's move on. Number 5. Zoom in. Cool. What mass in grams of calcium 2+ is present in 3.102 grams of calcium phosphate? Molar mass of calcium phosphate is 310.18 grams per mole. Okay? So what are we looking for? We're looking for a mass. We're looking for a mass of calcium in that compound. Okay? Let me, can everybody hear this thing keeps, it's interesting. All right. So for this one, I'm going to do it simply as a proportion. We know a molar mass, 1 mole of the substance weighs 310.10 whatever, 310.18 grams. So I'm going to do it where here's my given, which one did I write it? 3.102 grams of calcium 3P04 over X grams of calcium 2+ equals 310.18 grams of calcium P04 over how many grams of calcium are in 1 mole of this compound? How do I find that? How many calciums are in Ca3PO4? 3. And what's the weight of calcium? 40.078. So multiply 40.078 by 3. Okay? In 1 mole of the substance, there's 120.3 grams of Ca. It's 120.3 grams of Ca. Cool? Everybody see where I got those? This is per 1 mole. This is per how much I have. Awesome. Now I'm just going to cross multiply and divide. So I cross this, multiply this, get this, you get, I'm going to try to save my space, 310.18x equals 3.102 times 120.3, and divide, and you should get, find it, 1.200 grams. Everybody get how I got that? Try it. Yes? Agree? No? Maybe? Awesome. Let's keep moving then. By the way, this is your time to ask questions. If you're unsure of something, ask. Don't be afraid. I know there are a lot of people in here, but still. Okay? Awesome. Let's keep moving. my page. Okay, next question. Chemical reactions are often studied at 25 degrees Celsius. What is that temperature in Fahrenheit? This goes back a ways. Huh? All right. So what's the formula for conversion of temperature from Celsius to Fahrenheit? Come on, somebody's got to know it. What? What? All right. Yeah. So the formula is Fahrenheit equals 9/5 or 1.8 times Celsius plus 32. That's our formula. Okay? Cool. Try it. Give it a shot. There's your formula. Plug it in. See what we get. I give you 30 seconds to put it in your calculator. All right, I'll give you a minute so I can figure out my mic problem here. Oh. That work? No. I do not like lavalier mics. There we go. All right, what'd we get? 77. Exactly. It's 77 degrees Fahrenheit. Okay? Conversely, what's the conversion factor for Fahrenheit to Celsius? Conversion factor from Fahrenheit to Celsius. If I were to go backwards. Exactly. Conversely, it's Celsius, here, Fahrenheit minus 32 divided by, well, it's multiplied by 5/9. That's the converse of that. Okay? And how would I convert to Kelvin? Come on, just yell it out. Say it. Add 273 to the degrees Celsius. It's the same thing. All right? Make sense? Awesome. All right, let's keep moving. The next one's a little more recent. What is the oxidation number of each atom in sodium perbromate? Work with your partners. I'll give you a minute and a half to do this one. Okay? Find the oxidation numbers of that compound. Awesome? And it's in the respective order there. I know the answer choices aren't quite clear, but you know. Give it a shot. Work with your partner. Seriously. Work together.
Because permanganate means there has to be like an extra.
Could you zoom in a little bit?
Yeah, I'll zoom in.
Because there's an 04 and it's just hard.
Yeah, there's an 04. I got it.
Are you having one tomorrow too?
I think there is one, but it's not mine.
No, it's not their guy.
It's somebody else.
Same room?
I don't know. You got to check the schedule. I only know what mine is.
I think it's 4.
What?
I think it's 4. Did you ask what time?
No, he asked what room.
We're using the same room.
Probably. It's either this one, Key West, or Pegasus Ballroom. All right, one more minute.
So with you having this today, you're not going to have the thing on Thursday morning?
I have an exam Thursday morning.
Oh, you do?
Yeah.
Okay.
That's why we do study union instead.
You have calc?
I have calc tomorrow, calc 2. That'll be fun. No.
Ready for it?
I'm ready. It's only 7 questions.
Multiple parts, I'm sure.
Yeah.
Yeah. Every time my calc one was.
All right, let's go over this. So, for oxidation numbers, there we go. I'm going to write this out big. NaBrO4. Okay. What's the charge on the oxidation state of oxygen in this compound? -2. Exactly. Oxygen is always -2 except for in which two cases? Exactly. In a peroxide or a superoxide. Okay? Realistically, I mean, again, anything I say, study, but still. You may see a peroxide H2O2, but that's about it. All right. What's the oxidation state of Na? +1. All right. So in order to find out Br, we have +1, we have X, plus X, then we have -8 has to equal 0. Okay, so we get +8. We solve for this. X equals, we have +8 goes to the other side, so we get +8, and then subtract 1, 7. +7. So, respectively, Na is +1, Br is +7, O is -2. So where's my +1 or +1 plus C -2? Here it is. Make sense? Because first thing, usually the one in the middle is the one you're trying to find out. Second thing, oxygen's always set. That's just a standard at -2. And group 1A metals are always set. So.
What about group 2?
Group 2, most of the time they're set. Just usually, most cases you'll see they're set. Okay? Unless they're in the middle somewhere. Unless there's a more complex compound, which I don't think you'll get. So. Cool. Everybody get that? Understand? Yes? No? Maybe so? Can everybody hear me? Kind of. I don't know. Whatever. All right. Awesome. Let's go to number 8. Let me move this down. That's number 8. Let me zoom out just a hair. There. It takes 11.2 kilojoules of energy to raise the temperature of 145 grams of benzene from 45 degrees Celsius to 70 degrees Celsius. What is the specific heat of benzene? Awesome. So, we're looking for specific heat. Specific heat. What is the specific heat? What specific heat? Exactly. It's the tendency for it to resist change in temperature. It's how hard it is, the amount of energy required to raise it 1 degree Celsius. Okay? So, I'm given it takes 11.2 kilojoules of energy to raise the temperature of 145 grams. So here is my Q I'm given. So I'm going to use Q equals, I'm given an M, C, which is what I'm looking for when my pencil doesn't break, C, and I'm given a change in temperature, delta T. Awesome. So now I just plug in and solve for my C. So I'm given 11.2 kilojoules equals 145 grams times C times my change in temperature. So what's 70 minus, if I'm ever off like that, let me know. If you ever can't see it, let me know. So what's 70 minus 25? 45. Exactly. Now I'm going to multiply these two together and then divide over here. So what's 11? Well, I could change, since my final units are in joules per gram, I'm going to change this to joules. So I have 1,200 joules equals 145 times C times 45. And when I multiply and divide that out, I should get 1.716 joules, that's a J, per gram Celsius degree, per degree Celsius. So my answer would be that. Make sense? Yes, no, maybe so? Awesome. I'll keep going. Number 9, calculate the mass percent composition of oxygen in Al2SO4, and that's a 3 there. I'll write it bigger. Al2S04, 3. That's what we're looking for. Okay? So, we're going to find out what is the molar mass of that guy. That's our whole. We want to find the percent. It's like, I always think of it, we're trying to look for the percent of the part per the whole. So, I need my oxygens, my mass of oxygen, O in grams, over Al2S04, 3 in grams, times 100 equals percent. Okay? So in this compound, what is my mass of oxygen? How many oxygens are there? 4, 12, how many? 12. I distribute this in. Let me move this up. We have O4, yes, but we also have a 3 out here, so there are 3 SO4 molecules. So 3 times 4 is 12. So what's 12 times the molar mass of 16? Times the molar mass of 16. It's 192. 192 grams of oxygen over, I know I'm running out of space here. What's my total molar mass of this compound? Go ahead, try it first. What's the total molar mass? Is it?
42.132.
It's 340. It's 342. I did this. It's 342.26 grams times 100 equals roughly 56.1%. Try that on your calculators. So the answer is D. Try that on your calculator, see if you get the same thing. Let me zoom out a little bit. Zoom out. We good? Any questions on what I did or how I got it? Questions? I put this on my sweat, on my jacket, or on my shirt. Oh, I don't even know what I'm saying anymore. All right, yeah. That's the mass of oxygen in the compound. So it's 12, since there are 3 SO4 molecules. You distribute in. It's 12 times 16. Okay? Yeah, I get you. Questions? Cool. All right, let's keep moving. Number 10. Solve the following to the correct number of significant figures, sig figs, with correct units. Awesome. So, what's the rule for multiplication? Sig figs. Can't hear anything. What is it? The least amount of decimal, or the least number. Yes, the least number. Cool. So when I multiply this across, I'm going to do it one step at a time. So I'm going to multiply the top across, I'm going to add the bottom, and then I'm going to divide. We'll do it step by step. Okay? So when I multiply the top across, this equals 8.33125 centimeters cubed. Okay? So, how many sig figs do I keep here? 2, exactly. Because this one has 2 significant figures. Does everybody see how I got the centimeters cubed as well? It's 3 things, 3 centimeters, multiplied together, you get centimeters cubed. Okay? And I keep these 2, but I'm not going to. The main thing here I'm trying to get, do not drop decimal places in intermediate steps. Just keep the number of sig figs it's going to be. So I know here I'm keeping those 2 places. We know there are 2 places in that. But I still want to be accurate on my final answer. So this is over. I know that's not the best description. I'm going to put that there just so you can see. Those are the 2 I'm going to keep. There are 2 there. Awesome. So here, I'm going to add these 2 together. What's the rule for addition? Smallest number of decimal places. Exactly. So we know there are 2 decimal places here. Cool. So we're going to end with 2. So when I add these together, I get 17.238, whatever, 238. So I'm going to underline these last 2, and I'm going to get centimeters. Because, again, we're not multiplying the centimeters, so they stay the same. Awesome. Continuing, when I divide these, what am I going to do? What's the rule for dividing? What is it? Exactly. It's the same as multiplying. It's the lowest number of sig figs. So, which one has more? All of these, which those all count, or this one? I'm going to end with 2 significant figures. Okay? So, also what you have to pay attention to is there's 1 centimeter in the bottom and centimeter cubed at the top. So, this gets canceled, and that becomes a 2. So, when you divide this, you get 0.4833 centimeters squared. And I'm going to keep these 2. So your final answer is 0.48 centimeters squared. Questions? Everybody get it? Yes? Yes? Awesome. Let's keep going. All right. What is the concentration of iron 3 chloride in a solution prepared by dissolving 35 grams of FeCl3 in enough water to make 275 milliliters of solution? Okay. So, I'm going to start by converting my given mass to moles. I can't do anything with it in grams. Okay, we're looking for a concentration. And here, we're looking for the molarity of the solution. What's the formula for molarity? Exactly. Big M, molarity. I'm going to put it over here. Big M, which is molarity, equals moles of solute over liters of solution. I know you can't really read the solute, but whatever. Moles of solute over liters of solution. Awesome. So I need this in moles in order for me to do anything with it. And this one, I'm going to need in liters. But for now, I'm just going to start converting this to moles. So we start with 35.0 grams FeCl3. What is the molar mass of FeCl3? 162.20635, whatever, somewhere in between 206 grams of FeCl3, 1 mole FeCl3. When I multiply and divide, I get 0.2156 moles. Okay? I'm going to kind of box this out. Awesome. Of FeCl3. All right, so there's my moles. Now, I need this in liters. So I'm just going to move the decimal place over 3 places, so I get 0.275 liters of solution. See where it says solution? Solution. Awesome. So we know molarity equals moles of solute. This is our solute. 0.2156 moles over 0.275 liters. And that equals 0.785 molar FeCl3. Good? Questions? If you have them, ask them. Trust me. Otherwise, I'll keep moving. Yes? So you want me to leave this up or slide it up or what? Move it? Okay. I'll move this up. This one got cut off a little bit, but the answer choices we'll figure out after. This is number 12. I'll fix that. I'll just do the answer, show you the answer choices on the next page after. Just got weird in a PDF form. Okay. For a particular process, we don't care what it is, that is carried out at a constant pressure, Q equals 125 kilojoules, and W is negative 15 kilojoules. Therefore, all right, we're looking for our H, delta H value, and our delta E value. Okay, so what, in this case, what is the formula for delta E? Delta E equals Q plus W. Is there any work in this equation? Yes? No? Maybe so? Yes. It's given. W is that, and Q is that. So, delta E equals Q, 125 kilojoules minus 15 kilojoules. Delta E, or E in this case, equals 110? 110 kilojoules. That's our E value. Now we're looking for our delta H, or our H value. Okay? In this case, well, what is the formula for H, delta H? Huh? What is it? Change in E plus W equals Q. We're looking for delta H. H. I'm going to write it in a different way. H equals, I'll move it. Yeah, I got you. H equals Q plus, we're looking at constant pressure, it's negative V delta P. Okay? Q plus negative V delta P. Is there a change of pressure in this? It's given at a constant pressure, so we ignore it. Okay? So our H is equal to Q, and we're given our Q. So H, we know E, I'm just going to put here, E equals 110 kilojoules. H equals 125 kilojoules. Okay? And the answer to that on the next page is C, for those following along. Okay? Questions? Questions, questions, questions. All right. Let's keep it moving. All right. This goes there. 13. When 30 grams of benzene react with 65 grams of bromine, 42.3 grams of bromobenzene are obtained. What is the percent yield of bromobenzene? There's the reaction, and the molar mass is that. Okay. So, what type of problem is this? Percent yield, exactly, it's given. We're looking for what the percent yield is. Awesome. So I have a given. First off, before we can find our percent yield, what do we have to do? We have to find the limiting reactant in order to find what? The theoretical yield. Because percent yield is actual over theoretical times 100. So I'm going to write that down. Percent, this is going to break again. Percent equals actual or theoretical times 100. That's our percent yield formula. Now we need to find our theoretical yield. We have our actual yield. There it is. We found that. Sometimes I get a question, how do we find our actual yield? You don't. You have to find it in a lab. This was found. Cool. It'll be given. Awesome. So, benzene, which is 30 grams, and reacts with 65 grams of bromine to form 43 grams of bromobenzene. So I'm going to go from product to reactant, reactant to product. Jeez, it's been a long day. From each reactant to find out how much can be made. So I start off my table, 30 grams of C6H4. I'm going to box this again. Our molar mass is 159.8 grams. That's C6H6, my fault. 1 mole. We're going to use our mole ratio, which is 1 to 1. In these types of problems, in your test, make sure they're balanced. This one is balanced. Make sure, first step, check to see if it's balanced. Otherwise, it'll totally screw up your numbers. Okay? All right. We get 1 mole C6H6. It's 1 mole C6H5Br. Okay? So now we need to find it in grams, though, so we're going to go to the next step, which is 1 mole. I'm going to run out of room. Equals the molar mass of bromobenzene, which is given, wherever it's given, 157 grams. And that equals, I have my numbers here, 60.384 grams. Okay, there's our yield 1. That means nothing. We got to get our yield 2 in order to figure it out. Okay? So our second one, I'm just going to go into this because it's a conceptual question. Our second one, we're given 65 grams of bromine, molar mass of, actually scratch that, I messed up the molar mass on this one, I was reading the wrong number. Molar mass on benzene is 78.0 grams, roughly. And this one's 159.8 grams, 1 mole. 1 mole of Br2 goes to 1 mole of bromobenzene, C6H5Br. Now I need my grams. We get 1 mole. I'm sorry for the lack of space here. If you can't read something, let me know. Equals 157 grams of bromobenzene, which equals 63.861 grams. Okay? So which one is our theoretical yield? It's a smaller one. Exactly. So on your test, when you do this, cross out the bigger one. I don't care about it. Cross it out. I'm not going to use it. I mean, maybe for excess, but you can do it a different way, which is how you guys were taught. I don't care about the bigger one. You just get confused with it. Go with the smaller one. Here is our theoretical yield. So, in order to find our percent yield, we use this formula, which I wrote up here very sloppily. Percent yield equals actual over theoretical times 100. Okay? Yeah, I can zoom in a little bit. I'm running out of space. Let me zoom in. There. Awesome. Okay? So percent yield, I'm just going to put percent, equals actual. What's my actual yield? 42.3 grams over theoretical. What's my theoretical? 60.384 grams times 0, 0 equals 70.1%. And the answer choice is A. I'll zoom out a hair just so you can see the whole thing. Questions? Yeah. What? Because that is how much can be produced. Each one shows how much can be produced of bromobenzene of each reactant. Okay? If I have 3 pencils but no lead in it, it doesn't work. So I have an extra 3 grams that can't be produced by the other one. So I go with the smaller one that can be produced by both. Okay? It's like if you have 5 wheels to a bike and 6 frames, how many bikes can you make? Can't make that many. You have excess of each. You have 1 wheel left and 1 frame, whatever, or a couple frames, whatever. There's your answer. Questions? How many feel comfortable with this? We got 1, 2. We got 2. That's encouraging. Okay. That's encouraging. I will say there is a good YouTube site. If you go on my Google site for SI, UCF-SI, look up my name, Sean. It's under Chemistry 1A with Patino. It says Shark Chem, which is the YouTube link. It's my old chemistry teacher. He has everything you'll go over in the next 2 semesters. Okay? Okay, cool. He's including this. He'll walk through it. Awesome. Let's keep moving. Let's keep moving, keep moving. Otherwise, we're not going to have time. What number am I on? 14. How many protons, neutrons, electrons are in a bromide ion Br? I'll write that bigger, or I'll zoom in. Br79. Yeah. Let me read my thing here. 79 minus. Geez, that's hard to read. Let me zoom out. Okay. I'll write this bigger here. It's 79 Br minus. Okay? Take a minute. Do that problem. Okay? Ask your neighbors if you don't know. All right? Seriously, work on it. I'm going to ask for answers. Br79 minus. You got to look at the periodic table. Hint. This goes back to week 2, I think. Week 3, something like that. I don't know. All right. Let's go over this. So we have Br79 in the periodic table. In our periodic table, what's the atomic number of Br? 35, exactly. Atomic number equals 35. Okay, what is that number? What is that number of? That's the number of protons. Number of protons does not change per element. What can change? Neutrons and electrons. Okay? So let's find, this is number of protons, so we can eliminate most of these choices actually. Geez, that's most of these choices because we know that it's one of those two because we have 35 protons. How many electrons do we have? 36. Why? Because it's a negative, so we add 1 electron. So we know it has to be this, but let's confirm it. So we have 36 E minus. So how do we find neutrons? Good. Yeah, you subtract the mass number, which is this, minus the atomic number, which is 35, and you should get 44. Does that make sense? Periodic table? Cool. We good on the periodic table? Awesome. I was waiting for a yes. All right. Let's keep on moving. How many sodium ions are contained in 99.6 milligrams? You can't see this compound. It's Na, I'll zoom in. Na2SO3. Na2SO3. How many sodium ions? Okay? So we're going to basically just go into how many sodium ions using our moles, or our number of ions per compound. So we're going to start with our given, 0.0996 grams. I converted to grams, yes. I just like it in grams rather than milligrams, just personally. You can start in milligrams, but, you know. Grams, okay? That's grams of the whole. What's the atomic mass of this guy? Molar mass. Not atomic mass, molar mass. I have it here for, let me find it. It's 126.1 grams of Na2S03. I'm gonna, is it okay if I erase this stuff? Because I'm gonna run out of room. Awesome, I just wanna make sure I'm not, like, you know. Okay, 0.0 whatever grams, that's our given. Here's our atomic mass of this guy. It was 1 mole of Na2S03. Awesome. Come on. Na2SO3. Okay, so how many moles of Na are in this compound? 2 moles. Exactly, so we're going to use a 1 to 2 mole ratio. Well, actually, you know what we can do? You can do it one of 2 ways. I'm going to do it to where I'm going to convert this to atoms first. So I'm going to go 1 mole Na2S03 equals 6.0 to 2 times 10 to 23rd. Well, this is molecules, but I'm going to put atoms. atoms of this. Okay? So in one atom, or not atom, it's molecule, but you get what I mean. It's just, I don't want to write out molecule. In one molecule of Na2S, S03, how many sodium molecules, or how many sodium atoms are there? 2, exactly. You could do it before or after. I just did it on here like that, so that's why I kept it. 2 atoms, Na. Okay? So we multiply this across, and you should get 9.519 times 10 to the 20 ions, or atoms. They're ions, they're charged, but still. So your answer is D. Questions? You can do it one of 2 ways. I started doing it one way, but I had it done on the answer key the other way. So you can go moles and then convert to atoms, but I just went the other way. All right, it doesn't matter. Questions? All right, let's keep going. (16) Given 4NO2 plus this reaction with delta H this, find delta H for NO2. It's basically the reaction flipped and divided by 2. This is kind of a mini Hess's law question. So we have a delta H. This is our given delta H for this one. This is our given delta H for this one. This one's divided by 2 and flipped. So what happens when I flip the reaction? Hey guys, can we keep it down a little bit? What happens when we flip the reaction to the sign of delta H? It flips. Exactly. Flip the reaction, flip the sign. Okay? So since I flipped this, I'm going to flip the sign. So this is our temporary delta H equals 110.2 kilojoules. What else is done to this one? It's actually divided by 4. See? You have 4 moles here. Since we flipped it, yeah, you have 2 moles here. Never mind, my fault. It's divided by 2. Yeah, we flipped it. It's divided by 2. There's 2 here. We're going to 1 here. So we're going to divide our delta H by 2, and you should get D. Okay? Just flip the sign, flip the reaction, flip the sign, and then divide or multiply by the number it's multiplied by. Okay? Questions? Yes, no, maybe so? Awesome. Let's keep going. What is the net charge for an ion with 33 protons and 36 electrons? Take 20 seconds to figure this out. 20 seconds. Net charge for an ion with 33 protons and 36 electrons. How many positive charges are there? 33. How many negative charges are there? 36. What's the difference between the two? Negative 3. So the overall charge is E, negative 3. Questions? Awesome. Let's keep moving. What mass of KOH is needed to make 400 milliliters of a 0.725 molar KOH solution? So we're looking for mass. Okay? This is number 18. So we know big M equals moles over liters, if my pencil will work. Moles over liters. Okay? So we're given a big M, so I'm just going to plug in what I know. 725 molar equals moles, which is what we're looking for. Over liters, we have our liters, which is 0.400 liters. Multiply across, looking for moles and then eventually mass. So which equals moles, well, I'm not going to put an equals there, moles. Moles equal 0.29, that's KOH. Okay, 0.29 moles of KOH. Now I have to convert to grams. 0.29 moles KOH. 1 mole OH goes to, let's see, 56.1 grams. 0.1 grams KOH equals 16.269 grams KOH. This is what I get for buying cheap pencils. 16.3. Where? Yeah. I'll zoom out a hair. Make sense? I just did my molar. I had a concentration. I found my number, my amount of moles, and then converted to grams. Okay? Awesome. 19. Calculate the number of moles in 0.901 grams of water. Go for it. Take a minute to do this. You can work together. I don't think you'll need to on this one, but we're looking for moles. Yeah. We plugged in to this formula. We had our concentration here, which is here. So then I plugged it in there. We have our liters here, 0.4 liters. So we solved for moles, and we got 0.29 moles. Okay? And then we just converted to grams using the molar mass. Okay? Make sense? I plugged into this. I just multiplied across, and then you get it. You just solve for moles. You solve for moles. So you multiply both sides by 0.4 liters. Those cancel. You multiply this one by 0.4. Okay? And you get 0.29. Okay? All right, what did we get for number 19? C, exactly. 0.0500 moles. Okay? None of the other ones would really make that much sense. So, okay, do I have to go over this one? Yes, no? Can I go over it? Yeah. All right. So I'm going to convert, see this, 0.901 grams H2O. The molar mass is 18.02 grams of H2O. 1 mole H2O. Multiply across, and you get 0.0500 moles H2O. Okay? Cool. Let's keep moving. Okay, number 20. How many Cu atoms are contained in 869 grams of copper? Okay? It's almost identical to half of them we've been doing. So, start out our same thing. Or 896, my fault. 6 grams Cu. The molar mass of Cu is 63.55 grams Cu. 1 mole Cu. 1 mole Cu goes to Avogadro's number, which is 6.022 times 10 to the 23rd atoms atoms. Can you see that? Awesome. And that equals 8.49 times 10 to the 24th. Okay? Questions? Avogadro's numbers, 6.022 times 10 to the 23rd. Okay? Yeah. I'm going to post this one's a little neater. I'll post the solutions. It's the exact same thing. Okay. 21. The following ions, Ca2 plus, NaNO3 minus, Na plus, SO4, SO4 2 minus, are placed in a test tube. The precipitate that forms is, if you're in Patino's class, it's simple solubility rules. You write out this side, you use your solubility rules that will be given you on the test. So I'm going to write out what's given. Ca2 plus O3 and A plus S04 2 minus. These are given. So according to one of the rules, we know it's going to combine positive and negative, or positive and negative, same thing, or opposite. So I know that CaS04, when it combines, it is insoluble. So the answer is D. That's just solubility rules. Okay? That'll be given on, the rules will be given on the test. I don't have my copy of the rules here, unfortunately. Okay? Just look through the rules and see. I don't know for some of the other professors if they do solubility. Yeah.
Like it says on number 5, all SO4 2 minus are soluble except for PB2 SO2.
There's an exception for, it's SO3. SO3. It should be SO3 or SO4. I'll get back to you. I'll get back to you on it. But okay? I want to move on, but I'll definitely look it over again before I post solutions. Okay? That's the marked one.
Yeah.
Okay. Let's keep going. Yeah, I think it's supposed to be SO3. Yeah. SO3. I'm going to change that to SO3. And we're good. Awesome. All right, let's keep going. We're given a reaction. Given the standard enthalpies of formation, calculate the delta H for this reaction. So how do I calculate enthalpy of formation? How? How in general? I'll say it. I'm not my time. I got you. It's sum of the products minus sum of the reactants equals delta H. Okay? So I'm given enthalpies of formation here. Here are my products, here are my reactants. Actually I have extra room here. Awesome. So, products. What's a product here? CO2. I have a coefficient here, so I need to multiply this by 4. 4 times CO2, which is negative 393.5, plus another product, which is 2 times H2O, which is negative 241. Geez, I'm having problems reading today. 241.8 minus reactants. I'm given 2 times C2H2, 227.4. Does oxygen by itself have an enthalpy of formation? No, it's elemental. It does not. You can't react things to get an element. I mean, you can, but This occurs in nature. Plus 0. Okay? So when I work this out, I get C. Okay? Yeah. I can't hear you. What? Last two you have to make negative. Where? Oh, right. Because it's on the same side. No, it's, these are negative. Those are negative. This one's a positive value. Does that make sense? Yeah, they're kind of scribbled in there. Okay? All right. What is the average atomic mass for element X? Okay? So I'm just going to go into this. You do your percent as a decimal, 0.7899. We're looking for the average mass of this element, okay? We have some isotopes here, and we want to find what's the average. So we have our percent abundances too. So we use our percent as a decimal times the mass, which is 23.985, whatever, plus 0.100 times our atomic mass, which is 24.98584, whatever, plus our last percentage, which is 11%, so as a decimal, it's 0.1101 times 25.98259. When we multiply those and add them all together, you get 24.31 atomic mass units. Any questions on this one? This is like how you calculate your final grade. 78% of the class are tests. 10% of the class are quizzes. 11% of the class are whatever, I don't know, homeworks. Okay? Add them all together, they have to equal 100%, and you get whatever. Okay? And there's your scores. If this was percentages on a test, this would be a huge problem. You get 24% in the class. Make sense? All right, let's keep going. Balance the chemical equation given below and determine the number of milliliters of 0.003 molar phosphoric acid required to neutralize 35.0 milliliters of calcium hydroxide, of molar calcium hydroxide. Well, this is fun. This is a titration problem. Definitely fun. Awesome. So, balance the chemical equation below. Let's balance. C, Ca, 3. Cool, that matches PO4, PO4, 2. Got to put a 2 here. H3, 6 times 2, or 6 plus 2 is 8, so we need a 4 here. Is my balance incorrect? This is a 3, this is a 2, that's a 4. Does that look right? Yes, totally could be wrong. I just, doing it off the cuff. Number of milliliters of phosphoric acid required. So I'm going to use this equation in a titration problem. First thing, you have to find the amount of moles of something. I'm going to list out what I have. We have of calcium hydroxide, 35.00 milliliters, 0.00150 molar. We need moles. Question. And we're looking for the concentration of this one, but we know we have a number of balance equation given below to determine the number of milliliters of 0.3. Actually, we're opposite here. The number of milliliters required. This is this is a little different than the ones. Fun. Okay. we know we have, this is why we write everything out, 0.00300 molar phosphoric acid. We're looking for milliliters, and moles. Okay? Cool. That's what we're looking for. So, since I have a concentration in milliliters, I can find my moles using big M equals moles over liters. Fun titration problem. Moles, 0.00150 molar, and this is CaOH, OH2, equals moles, which are X over liters, which is 0.035 liters. Can someone do this out for me? I think it's going to be a really small number. It's 0.0. I'm just going to put it in terms of millimoles then. I'll put it in terms of millimoles. 0.0525 millimoles. Is that right? 0.0525 millimoles of CaOH2. Okay? So now, this one I know I'm going to fill in my chart here. I really wish I would have made this with more space. I'll know for next time. 0.0525 millimoles, if you can kind of see that. Okay, so now we have moles, so now we can go from this one to this one and figure out everything else essentially. So, I found that 0.0525 millimoles CaOH2 where's my fraction? 3 moles of this. Actually, I'm going to keep it in. It really doesn't matter. It's just going to come out in millimoles. Can someone do that across? Did you find an answer? 0.035 millimoles. And this is of H3P0 or H3PO4. Okay? So now we can fill in our chart over here that we're making. 0.035 millimoles. So now, in order to find milliliters, we plug into our concentration molarity equation. I'm going to zoom out or move up or something. We get our concentration, 0.00300 molar, equals our moles. I'm going to convert back to moles. So these are millimoles, so I'm going to go 0.02345 mole over liters, which is our X. So when I multiply this across and divide, I get some really small number of liters, and I convert to milliliters, and I get 11.7 milliliters. Does this make sense? This is probably a difficult titration problem. This is definitely not the standard. Okay? Questions? Yeah.
Why did you go into millimoles?
Because it was I didn't want to write out the 4 zeros every time, so I just went millimoles. You don't have to. You never have to go to millimoles. Trust me, you never have to go to millimoles. I hate doing it. I just did not have the space to write out 4 zeros each time. Okay? Questions? I know this one's difficult. Titration problems are probably on the edge of the difficulty that you get on the test. This one is definitely on the edge because you're not looking for concentration in this case, you're looking for milliliters. Okay? It's just a little bit different on testing the concept. All right, let's keep moving then. Which of the following species sets have the same number of electrons? All right? And it's cut off. I'll fix it.
Thanks.
No problem. There's your species sets. A, B, C, and D, kind of. Which of the following species sets have the same number of electrons? Take a minute, figure it out. Use your periodic tables. Who came up with an answer? What? It's B. Yes, exactly. Same number of electrons we're looking for. Now that we know it's B, I can move this back. It is B. How many electrons does, what is this, I minus? How many electrons does I minus have? I minus. What? I mean, how many electrons, like, in the total? 50. 50 what? 54. 50, it's I minus. 54. How many electrons does neon have, or xenon, whatever it is? How many? 54? 54. Starting to see a pattern. How many does Ba2 plus have? 54. Exactly. Look at the periodic table, look at the charge, add or subtract. Let's keep moving. I kind of want to get to your questions. Here, I'll leave the choice up to you guys. Do you want to finish this packet, or do you want to go into your questions? Otherwise, I can stop 15 minutes early. I could try to get through the rest of this in the next 15 minutes, and then stop, and then take your questions. What? Finish this? Stop. What? Raise your hand if you want to finish. Awesome. That's overwhelming. Let's keep going. (26) NO is made from the oxidation of ammonia. How many moles of NO can be produced when 1.90 moles of NH3 ammonia react with 3.50 moles of O2? Okay? So we're looking for NO. So we're going to go from each one of our givens, each one of our givens to product. And this is very much a limiting reactant problem. We're trying to figure out how much can be made. So I'm going to use my givens. 1.90 moles NH4 4 moles NH3, you're right. NH4 moles of NH3 go to 4 moles NO, which equals 1.90 moles. That's our first one. That does not mean anything until we find our second. So we start with our oxygen, our other reactant. 3.50 moles O2. 5 moles O2. 4 moles goes to NO equals how many moles can be produced? We can get 2.81 moles. What is our theoretical yield? 1.90. This one is bigger. I do not care about it. This one I care about. So theoretical yield, that's how much NO can be produced. 1.90. Questions? It's like the one we did before. Cool. Let's keep going. What are the spectator ions in a reaction between aqueous phosphoric acid HP04 what is it? Phosphoric. Wait. What did I write before? Oh yeah, whatever. HC, oh, perchloric. I'm reading wrong. HClO4 and aqueous potassium hydroxide, KOH. So it's a double replacement reaction, so we're going to get H2O plus KClO4. Okay? So which one, here's our states, AQ, AQ. Is this aqueous, liquid, solid? In this case, it's liquid. This is aqueous. Okay, so what are the spectator ions? It's whichever one make up the aqueous compound. H2O is what we form. This is a acid-base titration. This is aqueous, so it does not form in solution, so our spectator ions are K plus and ClO4 minus. Yeah?
How'd you get the right side of the equation?
It's a double replacement. So we have a positive and a negative side on both of those. They just switch partners. So we have H plus goes with OH with minus, you get H2O. And then you're left with K plus and ClO4 minus. And they get KClO4 aqueous. It doesn't, you check your solubility rules to see if it forms, if it precipitates, which it doesn't. So they just float in solution. Okay? Awesome. Let's keep going. Yeah. Aqueous means that it's broken apart in solution. So there's K's over here in this. That doesn't actually form. That's just what we write in our reaction. It's still those two parts floating around. Okay? With, yeah, exactly. If it was a different reaction, not an acid-base one, it's whatever forms a precipitate or a liquid, like water. Spectator ions. No, the opposite. Yeah. Yeah. Yes, what are still floating around. They just watch the reaction. Yeah. What? The one that do not, the ones that form the aqueous ion, aqueous solution, are spectator. The ones that form in either a liquid or a solid are the reactants. They actually happen. So everything else is spectator. Okay? Yeah, when it forms a precipitate, that's what's actually reacting. But in this case, it doesn't actually form. It's still aqueous in solution. Okay? Awesome. Let's keep going. 606. All right, what is the molecular formula of a particular compound if its empirical formula is that and its molar mass is approximately 51 grams? Okay? So in order to find molecular formula, we find mass of the empirical formula, or mass, yes, we find our mass of the empirical formula, which H, or NH2Cl equals, our mass is 51 grams, actually. That's our mass in that, and this is our measured mass. So we do molecular mass over empirical equals ratio. And that ratio is what we multiply it by to get our molecular formula. So we have our molecular mass, which is 51, over our empirical mass, which is 51, equals 1. So we multiply the whole thing here by 1, and you still get NH2Cl. So the empirical formula is the same as the molecular formula in this case. Cool? Cool. Let's keep going. Determine the delta H for the following reaction. This is a Hess's law problem. You try, let me move down. You try to match. It's the Simon game. You want this reaction to match with those two and the others to cancel. Okay? So what I'm going to do is I'm going to flip this one. So I flip the sign, multiply it by minus, and then I still have to multiply this one by 2. So our new reaction is 2O2 plus 2S forms 2S02. This should be a 2. No, we're good actually. We're good. 2S02, this is this reaction, plus O2 forms 2S03. So when we cancel across. So these are the only ones that have to cancel. Add the rest. We're left with 3O2 plus 2S forms 2S03. Does that look like that one? Yes, it's the same thing. So we multiply our number here by minus 2, and we add it to this one, and we get negative 791.4. Okay? So whatever you do the reaction, you multiply by the number, and then you just add the numbers at the end. Okay? I'm seeing confused looks. I can go into this more if you want.
What if one completely cancels out? You still add it or not?
If one,
Would that not be a case?
it won't be a case. It's just this. I mean, actually, no, it won't be a case. It'll be given if it needs to be in there.
Oh, okay.
Okay? This is a Hess's law problem. All right, let's keep moving. Number 30. It is a balancing problem. This one is 4, this one is 3, and this one is 2. You guys know how to balance, right? I don't have to go into this. 4, 3, 2. C. Okay, 31. How many grams of NaN3 solid are required to form 5 grams of nitrogen gas? So essentially, we go backwards. We go from our given to what we're looking for. Okay? So we're given 5 grams. It's too high. There we go. 5.00 grams, N2. Molar mass of N2 is 28 of N2. Yeah. 1 mole. N2. 3 moles. N2 goes to 2 moles. This pencil. NaN3. I'm looking for the mass in grams, so I still have to keep going. Unfortunately, I'm out of space, so I'm going to show this copy. 5 grams of N2, 28 grams. N2, 1 mole, 3 grams, or 3 moles of N2, mole ratio to 2 moles. 1 mole NaN3 goes to 65.0 grams, which is the molar mass of that, and you get 7.75 grams. Make sense? That one's a little clearer. Yes? Awesome. Can I move this, or are you still writing? Still writing. Awesome. I should not have made this review this long. Next time, I will know. Yeah. Who's final? Patinos, 50 questions. My guess is 10 per chapter. We did 5 chapters. That's about my guess. He's been known to take questions from this, so just letting you know. Like half your quiz, some of your quiz questions, if you recognize that one, see, so they come from this essentially. Well, I don't know. Some of them have come from this in the past. Okay, what is the correct formula for an ionic compound that contains magnesium and fluoride ions? We already did something like this. Can I skip it? We did, this was like the first question we did. Yeah. Fluoride by itself is the ionic form. IDE, when it's Fl minus, it's just a negative ion. Doesn't matter. But there's your short answer. Do I need to go over this? No, yes, awesome. You take, let me scoot my page over. If you take 10 milliliters of concentrated ammonia, which has a molarity of 14.8, that's really concentrated, and dilute it to 0.5 liters, what will be the concentration of the dilute solution? I'm just going to show this. We're using our concentration dilution equation. M1V1 equals M2V2. 14.8 times 0.010 liters equals M2, molarity 2, which is what we're looking for, times 0.510 liters. Actually, it should be 0.500. My fault. 0.500 doesn't make that much of a difference. When you multiply these two and divide, you get 0.29, it's 0.296 molar. Okay? Does that make sense? This is the molar dilution equation. Yeah. What? M1V1 equals M2V2. This one. Where am I? There. M1V1, molarity 1, volume 1 equals molarity 2, volume 2. They're multiplied. Okay? Next one. What is the formula for ammonium nitrate? Ammonium, NH4, NO3 minus, just cross, NH4, NO3 minus. Reaction writing, or compound writing, we already did this. That's why I'm not too worried about you guys seeing the answer key. For the given reaction, we start with 5.50 moles of aluminum and 10 moles of chlorine. How many moles of chlorine will be left over at the end of the reaction? Okay? So, essentially, it already says that 10 moles, that moles of chlorine will be left over. So we don't actually have to find out which one's our limiting reactant. We already know aluminum's our limiting reactant. So we're just going to go with our 5.50 moles of aluminum to, using our mole ratio, to moles of Cl to show how much is used in the reaction. So from what's used, we subtract it, and we find out how much excess is left over, which happens to be 1.75 moles. This is moles. Make sense? This one's an easy question because it's already given which one's in excess and which one isn't. Okay? All right. Keep moving. Which of the following processes is endothermic? What is endothermic? Takes in energy. Takes in energy. So is the freezing of water. Freezing of water, the water is not taking in energy, it's actually losing energy. Combustion of gasoline, it's giving off energy. You blow something up, it gives off. The chemical reaction of a hot pack, often used to treat sore muscles. Endothermic. The hot pack is exothermic because you feel hot. It's giving off heat. Vaporization of rubbing alcohol. I like to say when you put water on a stove and boil it, It's endothermic because it changes state to a gas. You're putting energy into it. You're putting energy into the alcohol and it vaporizes. Okay? You just got to think of what's happening. Which of the following formulas is most likely incorrect? You can figure that out. That's not a super hard question. Can I move on? You'll have this answer key. I will upload it tonight to my Google site, probably a little later. I've got a final tomorrow, so I got to study. But all right, keep moving. Determine the empirical formula of the compound, which has the following percentage composition by mass. Okay, percent by mass. For percent by mass, we assume 100 grams total. So we convert our percentages to grams. We go to moles, okay, for each of them. We have carbon, fluorine, oxygen. We find how many moles, okay? Then we divide by the smallest one, just like in our combustion analysis or anything else like that. We divide by our smallest one. We get our numbers which have to be in the compound. C3F6O. We just assume 100 grams, turn it into percentages, or turn it into decimals, and then you go across, find out how many moles, and divide. Yeah. 0.6. When we convert 9.6 grams of oxygen to moles, that's moles of oxygen. That's the smallest. Yep. Okay. What mass, bless you, what mass of KCl is needed to precipitate AgCl from 15 milliliters of 0.200 molar AgNO3? Okay. So we're given 15 milliliters at that. First off, use your friend the molarity equation to find how many moles. So we have to find moles of AgNO3, which happens to be 0.003 moles of AgNO3. Cool. So then we use our mole ratio to go from one to the other. 0.003 multiplied across, using moles, multiplied by the molar mass equals 0.224 grams of KCl. Okay? Questions? I have like 3 more questions on the other one, but I will leave those to you because I have the answers. Now I will go over your questions for the next 9 minutes. Okay? Questions? And the packet on anything throughout the course. I can leave it up. I could turn to different answers on this. I could do something else. I like to leave the last little bit to you guys. What do you want to do? Anybody? Yeah, question. What? Required to neutralize. Does everybody know what's happening in a titration? Yeah. I'm telling you, the titration's probably the most difficult one you'll get on the test, exam, whatever. At this point, it all blurs together. In a titration, we're using this funny-looking thing called the burette. Okay, and this marker doesn't work. We're using this funny-looking thing called the burette. And we have a flask which has either an acid or a base. And this either has the acid or the base. We know the concentration of what's in here. Most of the time we don't know the concentration. In our titration problem we do. We just wanted to find out how much is in there. So we're dropping it in to get, in a titration reaction, for example, markers are dying. Cl plus NaOH goes to H2O plus H2O and NaCl, salt and water. We want to find when it's all H2O and NaCl. At that point, it's called the equivalence point. So we're neutralizing either the acid or the base by turning it into liquid water or with a pH of 7. That's when it says required to neutralize, we're dropping it in until the pH gets to 7, because that's the pH of H2O. Okay? So neutralizing is when the whole thing is reacted with. We're trying to get to the concentration of this. Usually, the one up there, it was a little weird. We were looking for milliliters of this.